Everyone, July the 1st. Alright, so another difficult one. So let's get that done and let's do this. But let's get this one done first. What do we have? Maximum number of achievable transfer requests. Okay, you have n buildings, number from 0 to n-1. Each building has a number of employees. It's transfer seasons, and some employees want to change the building they reside in. You're given an array requests, where requests is from and to, represents an employee's request to transfer from building I to building from to to. All buildings are full, so a list of requests is achievable only if for each building, the net change in employee transfers is 0. This means the number of employees leaving is equal to the number of employees moving in. For example, if n equal to 3 and 2 employees are leaving building 0 and 1 is leaving building 1 and 1 is leaving building 2, there should be 2 employees moving to building 0, 1 employee moving to 1 moving to. Return the maximum number of achievable requests. Okay, example 1. We have 5 buildings, right? N represents buildings. And the requests. So 0 need to go to 1, 1 need to go to 0, and 0 need to go to 1. 1 need to go to 2, 2 need to go to 0. Oh my god, 3 need to go to 4. So we say there are 5 number of achievable requests. How many achievable requests do we have? From building 0, okay, we just say from building 0, we will go out 0 to 1, 0 to 1. So from building 0, right? So we can say from building 0, we will out 2, and building 1, we will in 2. Right? And then building 1 will out 1. This one will in 1. Building 1 is actually out 2. Building 2 will in 1. Building 2 will out 1. Building 0 actually in 2. And building 3 will out 1. Building 4 will in 1. Thank you. The number of employees leaving is equal to the number of things moving in. So okay. So for building 1, we say which is good. If you're building this is good, we're building this is good, but these two are bad. So we say total requests is how many requests? Well, however many requests we're within this, right? The maximum number of requests. So which means everything related to 0. So 0, 1 is good. 1, 0 is good. 0, 1 is good. 1, 2 is good. And 2, 0. So 1, 2, 3, 4, 5. These are good. A, B, want to move to 0. Building 2, we have 0, Z, and then want to move to building 0. Building 4, we don't have any requests. So we can achieve the request of user X and B is swapping their place to achieve. Yeah. Okay. Have another one. Oh my god, it came from 0 to 0. So for this one, 0 out 1, in 1. Okay. Building 1, out 1. Building 2, in 1. And building 2, out 1. Building 1, in 1. So in this case, all 3 are good. Everything is good, so everybody's good. And in the last one, we have 0 to 3. So we have out 1 for 0, in 1 for 3, 3 to 1. So out for this, in for 1, and 1 out 1, and then 2. We have an in, and 2 out 1, 0 in 1, which means everybody involved is good. So what do you think? Can we just go run this? We do this in and out, we calculate, and to see which ones the net is 0, and then we go through the whole thing and see if the involved, well, would it be possible? What if I have 0 is good, but does that mean everybody involving 0 is good? That's the question. Like in this case, if I do another 2 to, I don't know, 2 to 1, okay? I do another 2 to 1, which means 2 is gonna lose another 1, right? Yeah. Just experiment. Let's say we take this for example, okay? And we do another 2 to 1. So when we do another 2 to 1, then this will be 2. So we go out 2, 1 going 1. Therefore, anything involving 1 and 2 will be bad. So in that case, 0, 3 will be good. 3, 1. How do you know if 3, 1 is good? And in this case, is the maximum transfer still 4? I feel like still 4. Is it just the last one fail, right? Actually, let's check. Is it still 4? It's still 4. Which means we just, okay. So we line up everybody. So we find out, it doesn't really matter. Like if I have 3 in to 0 and 2 out, which means we have 2 is still going to be good for 0, right? So which means 0 can accept 2 in and 2 out. Yes, 0 can accept 2 in and 2 out. And then, so in this case, 0 can accept a 1 in and a 1 out. So how would you do this? So from 0 out, okay. So 0 out, I can record 0 out 1 and somebody in, right? And maybe we can just do this. But then how do you know how many? Right? Requests have 16. I have 16 requests. From this to this, from this to this. So yeah, what I know is 0 I can go 1 out. Then we can actually say from 0, who do we go out to? Right? From 0, who do we go out to? So we can have something, this 0 go out to those. And let's say we can only achieve part of it. So we can say maybe we succeed 1. Okay. Yeah, I think maybe this is also like brute force. Try to go through all possibilities and then see how many requests you can achieve in every possibility. Basically, for each one, I can say, if 0 to 3, if it's correct, and then we try to see how many requests we can go. If we say this is not correct, how many requests we can go, right? So if 0 is 3, we accept. Then in 0 we have -1, right? And 3 we have a +1. And then we do 3, 1, which is, yeah, so it'd be 2 to the 16th. 2 to the 16th. What's 2 to the 16th? That seems to be a giant value. 2 to the 16th. That's actually not a giant value. So maybe 2 to the 16th will work. Let's give it a shot. Basically, for each one, I just do two possibilities. Either it's good or it's bad. And then at the end, we just see if we get a result we want, right? Okay, so we can say net, right? Net gain equals the default dict. Right, we can say default dict int. So we have index and we do, what do we do? How many has succeeded? Let's do num success, right? Achievable. Num achievable. And then we'll return, no, we don't return anything. And we have a self.res. So for each one I can do two, either I do it or I don't do it. If I do it, then I say, so first we say if index is equal to n, right? Then we say self.res equals maximum self.res and num achieve. Else, then we say in current, we can first say do the current request, grant the current request. If we do that, then we basically say net gain. We can say ft equals requests index, right? So net gain this will be minus equal 1. Net gain t will be plus equal 1. Then we do solve. Index plus 1. Num achieve plus 1. Right? Num achieve, actually we have to check. Right? We say if everybody has to be 0, right? If how do you check everybody is 0? Well, if they multiply, no. We have to go one by one. If all for v in net gain dot values, v is equal to 0. If everything is 0, then we do this. Otherwise, we don't. Right, we'll solve this. So that's, and after that, we need to take them off. So plus equal 1, minus equal 1. This is backtracking. Backtrack. And then we say do not grant the current request. If we do not grant, we just num achieve. And we'll solve 0 and num achieve is 0. And then we'll return self.res. Let's see. So we have n requests, maximum n requests. Okay, looks to be solid. Try this one. There's a different test case. Looks to be solid. We run it. And we got it wrong. Output 1, expected 4. How is that possible? This is brute force. How is our brute force wrong? I have no idea why. Hold on. Hold on. Let's change this. For I in range n. Okay, net gain v, and again I is equal to. No. Still not right. Huh? Very interesting. Hold on, let me see. Print index num achieve and net gain. What do we have? Index 0, 1, 2, 3, 3, 3. Oh, sorry. Where did I do wrong? Well, for one thing, I never reached 4. I think maybe whenever this is all done, we can do. Hold on, maybe we shall. Yeah, I think this is not. You don't have to go through all the requests, but we want to go through all the requests. Yeah, we will go through all the requests. But what if halfway through you get the answer, right? What if halfway through you get the answer? Yeah, what if halfway through? And this one is 3, so you're supposed to do 0, 1, 2, right? 0, 1, 2. You see, this is good, 0, 1, 2. And this is good, 0, 1, 2. This is good, 0, 1, 2. So we just ground this. Hold on, 1 to 2, 1 to 2. 2 to 1, 1 to 1. 2 to 1, 1 to 1. How is this not right? I don't see how is from, right? Net gain from 2. I do this. I take, and each one I can also choose, right? When we're done, and then we say we don't take, which means from, we add it back. 2 we minus. Then we go on, say with this one we don't take. And of course this is not right. So I shall do this at every step, right? If net gain, and do this, and then we shall say if this is smaller than n, then we try. I agree, we shall do this, but this is still not right. So I can take 1, 2, adding a 2, 1, that's already 2 steps. Right, that's already 2 steps. I don't understand. How is this not right? Yeah, every time we check net gain, achievable, we start with 0, and then we start from this, and we decide from 2. So from will be negative, yes. But the first one is 1, 2. That is correct. Then I shall have you know what? I don't like this. This is we'll do I want to know why. I know what can work. Hold on. Let me do something that will work. That I know will work. I think it's just bit manipulation. Bit manipulation will work. It's all the possibilities, right? So we say for I in range 1 left shift n. That's all the possibilities, right? And then we have a res equal to 0. And now we just need to find out how many is 1, right? And then we just say for j, for state, that is a state for j in range n, which means we're going to check every single positions. We say if 1 left shift j and state, which means this one is taken, then I should say a net gain. Right? Net gain is default dict int, right? If that's the case, then net gain, then we can say ft equals requests j, and then net gain f minus equal 1, net gain j t plus equal 1. And then that's it. We go blah blah blah. Then we say if or for I in range n, actually we can use j again, net gain j is equal to 0, then we need to know how many. We just say count, right? That's count plus equal 1. Then res equals maximum res and count. And we go all this, then we return res. This shall be right. This is still not right. So this one is correct. How is that possible? Like, seriously, how is that possible? Oh, we need to do requests. We need to do requests. You did n. Dude. Come on. We need to do requests. I am pissed off. I am seriously pissed off. Got these two confused. Oh my god. I'm pissed off.
Are you in there?
No, you can come. Yep. Oh, it's slow. Very slow. Brute force bit manipulation. 2 to the m times n. Oh my god. No wonder it's slow. Yeah, then this one shall work as well. Just got this wrong. Where did you get it wrong? This is fine. This is not fine. This should be LAN requests. Yep, now we're right. This one might be even slower. I don't know. Huh. This one's faster. I don't know why. Why is this one faster? It's exactly the same. You go through all the states. Huh. Same brute force as solution 2, but mysteriously faster. Yeah, 2 to the m, because I have to go through all the states, and each one you have to check. But maybe, no, maybe. That's that. I mean, we can probably end early. Oh, well, we're looking for a maximum, so I don't know if you can end early. We can. We can end early. Let's do a solution 3. So we can end early if the remaining requests cannot produce even more achievable. Right? That's what we can do. So we can say if m minus index right, if m minus index, that's the remaining haven't tried. If this is already smaller or equal to self.res minus num achieve, then we just return. It's no possible, right? You cannot produce more achievables. Otherwise, we try. Let's see, 3. Maybe this one will get it slightly faster. Can I make it slightly faster? Yeah? Actually a lot faster. A lot faster. Alright, with this I'm happy. So with this simple, but yes, with a simple optimization, right? Simple optimization, we speed up even more. It's a good speed up. All right, now we can check backtracking. Yes, bit masking. Yes, I guess that's it. That was a good one. All right, so yeah, this is the one, right? Okay, so we done this. Move on. Let's try this one. Let's try this one. 28. Mark 28. Okay, make costs of paths equal in a binary tree. You are given an integer n representing the number of nodes in a perfect binary tree consisting of nodes number from 1 to n. If it's perfect, that's 2 times the parent, and this is 2 times parents plus 1. The root of the tree is 1, and yeah, exactly, that's what they tell you. Each node in the tree also has a cost represented by a 0 index integer array. Okay, that's fine. Where cost I is the cost of node I plus 1. Yes, you're allowed to increment the cost of any node by 1 any number of times. To the minimum number of increments you need to make the cost of paths from root to each leaf node equal. So in this case, hold on, let's take a look. In this case, what do we have? In this case, we have 1, 2, 4. What's this? It's 1 plus 5 plus 2, right? This is 8. This is a 1 plus 5 is 6. Alright, 3, 6, and 7. 1, 2 is 3, that's 6. 1, 2, 3, that's 4. Right, so 8, 6, 6, 4. So we are asking the minimum number of increments you need to make the cost of paths from the root to each is equal. Well, I mean, everybody is equal. Oh, okay. So when you're given this, we can say on this subtree, usually you consider subtree, right? So because your root are the same thing, to make this and this and this are these equal, this means to make subtree, make this and this equal, right? Because we can ignore this. And to make this subtree, we should make this and this equal. Yeah, so these two must equal. So 4 and 5 are not equal. So I think 4 you need to plus 1. Okay. Oh, really? 4 plus 1? Yeah. I think I calculated wrong. This is 9. 4 need to plus 1, right? Now we go to 2. And here you need to make these two equal. So this need to plus 2. Right? Now we go to here. Then we need to know the path. So if this plus 1, this one is 8. If this plus 2, 3, this one be 5. So this need to plus 3. So in total, we need to plus 1, plus 2, plus 3. That means plus 6. That makes sense, right? In this case, the same. This is just gonna, oh, this is 0. So what we're gonna do is on each subtree. All right, let's do this one more time, right? Let's do it one more time. You want all the paths to have equal. And we know all the paths have the same root at the beginning. So if you want the entire path to be equal, that means you want the two subtree to be equal, right? You don't have to consider root. Okay, then within this subtree, you're doing the same thing. You want every path to be equal. So you ignore the root, you say all the subtrees need to be equal, and you go all the way down until you get the last, right? You get the node, you get the leaf node, right? You get the two leaf nodes. Because to make this the kind of the last subtree, all the paths to be equal, this is already the same, right? So you need to make the two leaf equal. So you make the two leaf equal. You check that, you find out, okay, I need to plus 1 here, so you plus 1. And then you go back to this, you find out what is the path sum at this root, and tell you it's 8. You do the same thing here. You may need to make the two leaf equal. So you need to plus 2 on here. And then you go back to the root. You say, okay, what is the path sum at this root? So it's 2 plus 3, right? That's 5. So that's 5. Now we need to make these two subtree equal, right? And then we know the path here is 8. The path here is 5. So the two paths need to equal. So this side needs to plus 3. So we just, keep going up. Look wonderful. Keep going up until you find the root. Okay, so that's the solution, but how do we implement it? Well, we have a root. We got the left subtree. So basically, just left subtree, we want to know the path. The right subtree, we need to know the path. Yeah, that shall do. So we just need to know the path, the sum of the path on the left, and the sum of the path on the right. All right, so let's do this. We will have what are we going to have? We're going to have a result. So we need to keep track of the number of weights we're going to add. And in the def, let's call it solve. All right, so we have a node. Yeah, we'll call it index. Ooh, index, I don't like this name. Let's call it node. and we need to return int. So we return the sum of the path. Okay, the sum of the path of the subtree rooted at node, and it has to be like balanced already. Okie dokie. So what do? We start from this, okay, and then we need to know if this is the end, right? If this is the end, how do we know if this is the end? Well, we have n, which means this. How do I know? How do I know? Well, we say if 2 times node is my left, right? If this is larger than n, that means node is a leaf. Then we just return cost node minus 1. Otherwise, any other node 2 times is still within the range. Okay, then we're gonna say the left path LP, okay, LP L cost equals solve 2 times node, okay, and we have a right cost solve 2 times node plus 1. These two need to be equal, but they might not, so we say self dot rest plus equal to ABS RC minus this, right? So that's the amount you need to add to balance the two. Then we're gonna return the path of the equal path of the subtree rooted on this. So we're gonna do the cost of the current node plus the larger of the 2 nodes, so maximum this. So let's hope we start from 0 and the result is correct. Okay, let's see. This shall be 6 and this shall be 0. Okay, so n and cost. Minimum n and cost. Maximum recursion. Something is not right. Something is not right. What the hell? What did we do wrong? Solve 0. Oh, solve 0, my bad. Solve 1. Int is not iterable. What did I do? Oh, cost, node. What did I do? Int object is not iterable. There's no int object. This is a cost. What the hell? Huh? That is very interesting. What do we do? Cost plus maximum. Alright, this is not this. Okay, this is... Sorry. Got it wrong. Typo. Yep. That's that. So binary, it's not binary search, it's just, does that count as greedy? Right, does that count as greedy? No, I don't think it's, maybe we can count this as greedy, but the idea is to equate the cost sum of the 2 subtrees, right? Equate cost of 2 subtrees for all levels. Well, that's all I want to say. Well, What else can we say? We want to equate the cost of two subtrees. And the difference, okay, the difference of the current cost sum of the two subtrees is the additional steps we must take. That shall be it. And because every node is visited once. Okay, so that's that. We're ending at 4050. It's called 4050. Okay, I think I have capacity to do, let's do one more. Okay, probably can do one more. Let's do the stretch. Yeah, we hit. Maybe I can do two more. Let's do two more. I think I have enough in me for two more. Maximum sum with exactly k elements. You're given a zero-indexed integer array and an integer k. Your task is to perform the following operation exactly k times in order to maximize your score. Select an element m from nums. Remove the selected element from the array. Okay, add a new element with a value of m plus 1 to the array. Increase your score by m. Return the maximum score you can achieve after performing the operation exactly k times. Read again. Is to perform the following operation exactly k times. Select an element, okay, remove it from the array, add a new element with a value of this plus 1 to the array, and increase your score by m. Okay. Are you kidding me? You just sort m. You don't even need to sort m. You get the largest m, and you take that out, and you plus 1, put it back in. So in this one we get 5, and we plus 6 back in, right? And then you take 6 out, that'll be 11. You plus 7 back in, and you take 7 out, that's 18. You put 8 back in, and that should be it. So basically we find the largest, and we just do 5 plus 6 plus 7 in this case. This is just 5 plus 6, okay? They are just making it a little bit more convoluted than it requires, but it's fine. It's an easy problem, so you can see what they're trying to do. They're trying to confuse you. Let's do it in one line. So I need max nums, right? And I need, I don't know, can we say m? Let me try this. Max nums plus m plus k minus 1, right? Times k divided by 2. Let's see. Is this gonna work? Shoot. Maybe we do it this way. I don't know. I'm not 100% sure on how the walrus work. Oh, you put this one and it works. Okay, that's how walrus work, I guess. You have to put a parentheses on it to define it first. Okay, so this one is done. Yeah, I don't want to write anything for this. There's nothing to write. All right, one more. Okay, that's the last one for today. Find the prefix common array of two arrays. You're given two zero-indexed integer permutations a and b. A prefix common array of a and b is an array C such that Ci is equal to the count of numbers that are present at or before the index I in both a and b. Hold on, I'm going to do this one more time. A prefix common array of a and b is an array C such that Ci is equal to the count of numbers that are present at or before index I in both. Return a prefix common array. Ci is equal to the count. Okay, the count of numbers. Oh, I see, the count. So at this is 0. This will be 2 because 1, 3, 3, 1. It'll be 3, it'll be 4. Gotcha. 0, 1, and 3. Gotcha. Okay. Okay, how are you going to do this? Well, it's going to be a count, right? So, and we're going to go one by one. We can just do 2 sets. A set for A and a set for B. That's it. Every time we add something into it, we just count the size. Wait, no, not really count the size. We have the set. We have SA and SB. Okay, these are sets. So every time a new come in, every time we get 2 come in, and then we check if it's in this. Wait, hold on. How are we gonna do this more common ones, right? Common ones. So now we have 1 and 3. Okay. The next one I have 3, and the next one I have 1. How do you know how many common ones are in these two? Well, I can say, is 3 in this? I say yes. Is 1 in this? I say yes. But that doesn't mean anything. That doesn't count as 2. Right? We can just set this and set this. We do an intersection, which based on this is fine. But that's like O(n) squared, right? That's like O(n) squared. Let's solve it O(n) squared first, and then see if we can make it better. Make it better. There gotta be a way to make it better. Like if we know the common in the front, let's say I know the common is 2. Now I have these 2 coming in, right? Then let's say this one exists here, but it was not existing here. So when this one comes in, I check. If this is not in here, but is in here, that's +1. That's yes. Yes, if it's common, yes, so at the start is 0, right? And then if it's not in here, if these 2 are equal, definitely. If these 2 are not equal, then we check if it's in the opposite. If it's in the opposite, then we +1. If it's not, then we don't +1. Yes, let's do it that way. That I can do, I think, if it's correct, that is O(n). But of course, if you want to brute force this, I'm pretty sure you can brute force this as well. We're going to do SASB. It's just going to be 2 sets. Okay, rest is 0. And we say for AB in zip AB. Okay. If A is equal to B, res plus equal 1. Else if A in is B or B in is A, now we might as well just do this. If they are or this, else we just don't do anything. SA add A, SB add B, and we'll return the rest. Okay, let's give this a shot, see if we got it right. Shall be 0, 2, 3, 4. This one shall be 0, 1, 3. 0, 1, 3. 0, 1, 3. A and B. Find A and B. Is that right? Is this right? Oh, you've got to be kidding me, man. Sorry. Got a panned. I'll do 0. Rest minus 1 plus 1. Huh. That is interesting. Oh, I forgot to add. Else. Yep, so I gotta add this. That's not right. Oh, yeah. Hold on. Yeah, hold on. It's more complicated. If they're equal, okay, let's do one by one. If they're equal, we add 1, okay? And we say if A is in SB and B not in SA, right? So we say or this or B in SA and A not in SB. Okay, these add 1. Aleph A not equal to B and A in SB and B in SA. This is adding 2. Else. There we go. That. Hot shot. Give it a shot. There we go. Nice. Yeah, it's slightly more complicated than I expected. Use 2 sets to keep track of the numbers in each array. For each new pair of A and B, right? If they are the same, we increment the count by 1. If they're not the same, but one of them has been encountered by the other array, whereas the other number has not, we increment the count by 1. If both have been encountered by the other arrays, we increment by 2. For this, we can solve in O(n) time. one pass. Let's see. Oh, you don't even need a set. Scene. Oh my. Bit manipulation. It's the same idea. Similar idea. If one left shift A, which means if this one has been seen before, then we add the scene. But they only did one. They only did one. The second time we have seen the value, we'll increment. That's actually true. That's true. So if it has been seen before, huh. Yeah. Oh my god, this is smart. If I've seen it already. Yep. Oh my god, this is smart. And bit manipulation. I mean, we can. What's the 50? 2 to the 50. I'm not so sure about that. I just use a set. Scene. Right? We can say this is inspired by our beloved Lee 215. Okay, so the idea, right? The idea is that as we iterate through each pair of values in A and B, if the value has been seen before, that means it must exist in either A or B, right? Which means we have come to a point where it exists in both. I'm not sure if they explain well, but that's the idea, right? What this means is that we just need to count the moment when the value in A and B shows up the second time, right? That's what we need. So we have this, we have results, it's gonna be this, and we're gonna have current. Yes, we need to use current. Then we say for AB, yeah, we're doing the same thing. Yeah, I see why he's doing this for this, right? And then we say for V in AB, if V is in scene, then current plus equal 1. Alright. Then we say res.append current. And hold on, if V in scene, and then we say scene.add V. And then we return res. That's right? Yeah. You see that? We go through. If any time it has been seen before, that means it occurs previously. And because all the values are unique in the permutation for the two. So if we've seen it before, that means it exists in one of the array. And it's seen a second time, it exists in the other array. Then the value that's common to both is increment by 1. That's that. ON as well. ON as well, but it is simpler. Oh, we hit a 99%. Jeez, man. Alright. 1 hour. That should be it. I will see you guys tomorrow.